Course title. Course title. Problem solving. Course title. Essentials of problem solving. Topic. Graphical travel based solutions for trip planning in public transport graph. Presenter name Sheikh Firoz. Introduction. Importance of the trip planning. Graph representation of public transport network. Challenges in trip planning. Graph transversal technique in trip planning. Breadth first search BFT, depth first search DFS, Dijkstra algorithm, A search algorithm, and Bellman-Ford algorithm, Flood-Wash algorithm, bidirectional search. Real-world application and optimization time-dependent graph. Transfer alware route planning, graph construct techniques, changes student studies and practical implementation, urban survey system optimization, bus route planning and diagnostic vehicles, weights, integration of real-time traffic data, implementation strategies, data structures for efficient graph storage, areas of faster computing, handling dynamic changes in transportation networks. Conclusion and future directions. Advancement in AI based trip planning, roles to the machine learning in route optimization. Future trends in smart transportation. Introduction. Trip planning in public transportation is a crucial aspect of the urban mobility, aiming to provide users with most of the efficiency and convenient route planning. Public transports networking can be naturally representative by graphs and where networks and where the nodes and represents the transport stops and stations. This most of these technologies are used in AI tools like Google and some of the tracking mobile tracking applications and etc. Edges represent connections between stops and which can be have weight denotation, travel time, cost or distance. Finding optimal routes in these graphs involves graph transversal techniques, ensuring that the passenger reach their destination in short time possible with minimal transfer and cost. Graph transfer techniques in trip planning. Different transversal methods are used to compute efficient trip plans. Below are key techniques. Breadth first search BFS uses case finding the shortest path in unweighted graphs. Example minimal number of stops. How it works. Exploration all the adjacent stops before moving deeper into the network. Complexity. Example finding a subway route with a least number of stations transfers. Depth of first search DFS. Use cases exploring all the possible routes for the search source and destinations. How it works. Restrictively exposed routes are unique until a dead end is reached. Complexity. Examples finding a scenic or alternative routes. Dijkstra's algorithm. Uses case finding a shortest path in weighted graph. Minimal travel time or cost. How it works? It's a use to prioritize the unique add to expand and least cost node first. Complexity. Example computing and fast bus routes considering the travel time. A search algorithm uses a case fast pathfinding and heuristic optimization. How it works? It uses an heuristic function to estimate a distance to the goal. Complexity. by often faster than digitistic structs. Example, route based on real time traffic is a geographical distance. Bellman-Ford algorithm. Use case handles a graph with negative weights. Example, fare discounts and time penalties. Penalties. How it works? Literally, literally update path cross for edges. Competitively, example, finding an optimal fares with the time department pressing. Floral Warshall algorithm. Floyd Warshall algorithm uses case study. Pre-computing shortest paths between pair of stops, and how it works. Using a dynamic programming to compute shortest paths. Complexity. Example, static subway network route optimization. Bidirectional search. Using case study. Use case study. Optimizing shortest path search in a largest networks. How it works? Runs two simultaneous searches, one from the source, another from the destination. Complexity. Where the shortest path depth. Where is the shortest path depth? Example, large cities transit system navigation. Real world application and optimization. Time department graph. Public transport schedules a vary by time of day. Solution using time dependent Dijkstra algorithm. Transfer alware route planning. Minimize the number of transfers to improve the passenger convenience. Solutions. Modify a graph travel to penalize transfer edges. Graph contrastion techniques. Reduce a graph complexity while preserving optimal path. Solutions. Pre-compute key daisy transist hubs for faster lookup. Case study of practical implementation. Case study, urban subway system optimization. Problem, finding the fastest route in the subway network. Solution, logistic algorithm with real-time delay. Case study, bus route planning by dynamic weights. Problem, according of for real traffic conditions, solution say search is with time depart weights. Case study 3, integration of real-time traffic data. Problem, traffic congestion, alter effects, bus arriving timings. Solution, time dependent logistic with the dynamic edge updates. In implementation of strategies, data structure for the efficient graph storage. Adjacent list, best part of the graph typically transit networks. Typical for the transit networks. Priority quads. Essential for the Dijkstra's and A-star algorithms. Heuristic and fast computation. Landmark based ASR and pre-computes distance from the key landmarks. Transfer penalties. Weight station changes approximately. Handling dynamic changes in the transport networks. Real-time API integration updates adjust weight and dynamically. Predecisive modeling using machine learning to estimate delay. Conclusion and future directions. Advancement in AI based tip planning. Neural networks for demand forecasting. Reinforcement learning for optimal transport routing, and role based machine learning in route optimization. Clustering algorithm for demanding best based route planning. Adaptive learning for real time scheduling. Future trend in smart transportation. Autonomous public transit and AI optimal routes, blockchain for the disintegrate flame management. Final thoughts. A graph transversive techniques are essential for optimization of public transport planning, whether it's BFS or simple routing. Logistic for the faster route path or ASA of holistic driving efficiency. The right choice depends on the network needs. With real-time data and AI driving advancements, public transport can continue to evolve into smarter or more efficient system. Thank you.